Due to lack of appropriate GPU, no recordings of Unity will be showcased in this briefing. I apologize for this inconvenience, however, I am certain that enough information will be provided to prepare you for flight using the Albatross UAV. For this task, several CG positions were investigated to estimate a suitable balance between main and nose gear. To achieve good steering, approximately 8% of total weight of the aircraft should be placed on the nose wheel. With that restriction in mind, CG location was placed at around 37% of Mach. Therefore, this should be the utmost limit for operations with wheels on the ground. Additionally, CG was also calculated manually from the Unity data and plotted against actual CG values taken straight from the simulation. When compared, the methods are connected by a quasi-linear nature, meaning that they can scale almost identically. Therefore, both aircraft's mass and CG can be estimated based on the rear action measurements, although should be used with caution. Thrust and RPM values were taken off Unity data and were presented in the shown graphic. It can be seen that the static thrust scales linearly against RPM. The aircraft can be controlled using the controllers and associated bindings showcased in the figure. To achieve control effect set, the polarity must be turned on for the aileron, rudder, and elevator in the Unity file. For this section, we will consider two different free stream velocities, stall and max, and then three different CG positions. For the stall at 10 meters per second, angle of attack oscillates significantly after a change in the elevator trim setting. It also takes a considerable amount of time before reaching steady state. For Vmax at 27.7 meters per second, angle of attack's oscillation is reduced to minimum, and steady state is reached within seconds. It has also been proven, based on the showcase graphs, that the sign of the change in the trim of angle of attack is consistent with the sign of the elevator input, and that the aircraft pitch response is consistent with the change in lift on the tailplane. For the following graphs, the velocity was set at around 50 meters per second, whereas the CG positions were changed for each case. This is the response for CG set at 0% Mach. This is the response for CG set at 21% Mach. And this is the response for CG set at 32% Mach. It can be seen that between 0 to 21% Mach, the aircraft remains stable. Of course, for lower CG positions, this might be a problem of overstability. Therefore, it will be beneficial to move the CG to around 21% Mach for better maneuverability. After reaching value of 32% Mach, the aircraft pitched up significantly and almost immediately rolled to one side, becoming completely unstable. Based on these findings, the aftmost CG limit therefore would be at around 30% Mach, but most preferable position would be at around 27% Mach. Here, we can see the aircraft's response. Relevant data was then plotted in Excel, and the short period frequency and damping ratio for pitch at previously stated conditions were found. These were found to be much lower than the predicted values, most likely somewhat due to the differences in flight conditions. Here, we can see the aileron trim at 5 degrees, 10 degrees, 15 degrees, and 20 degrees. It was noted that for a constant aileron trim, roll rate changes with a change in aircraft velocity, with higher roll rates at higher speeds. It was noted that damping in pitch is much larger than damping in yaw, as the required time to reach steady state is much smaller for pitch than for yaw. The aircraft was also found to correctly roll to the right when yawing to the right. The larger the distance between CG and thrust line, the bigger the resultant moment will be created above the CG. As the default CG is 4 cm beneath the y-axis, the thrust will result in a pitch-down moment. If the CG is raised above the thrust line, the result will be seen as a pitch-up moment. To achieve the zero thrust pitch coupling, the CG position should be placed at around 2.8 cm below the y-axis. Here, we see the lift cross slope for different flap settings. The highest CL was noted at slightly below 1.2 at around 8 degrees angle of attack for a flap setting of 40 degrees. Here, we see the drag polar with flap settings at 0 degrees. Here, we see lift over drag graph for different CL values. The highest L over D value was found to be slightly below 15 at around 0.8 CL. Compared to the manufacturer's data, it is around half of what it should be. It was noted that changing the flaps angle did not result in noticeable differences. Here, we see the moment coefficient against CL at different elevator settings. The best performance corresponds to a CMM of 0, which happens when the elevator is trimmed at -15 degrees. Here, we see the moment coefficient for different CG locations. The neutral point can be found when the showcase functions become horizontal to the axis of lift coefficient. Based on that, it can be approximated that the neutral point would be between CG set at 25 to 50% Mach, with the most reasonable approximation set at around 40% Mach. Although not showcased, it has been proven that both nose gear steering and rudder input provide enough authority for maneuvering on ground. It was also found that the aircraft was able to turn at high speeds during Unity simulations. It should be noted that some of those velocities would likely be unobtainable, as the aircraft would be likely to tip and crash. Additionally, such speeds would put immense amounts of pressure on the wheels and gears, making it possible for the aircraft to collapse. It was found that the minimum unstick speed without flaps deployed was around 26 meters per second. With flaps deployed, the speed dropped to around 20 meters per second. As the velocity is supposed to be at around 10 meters per second, these values differ greatly. It was noted that in order to achieve steady level flight at a cruise speed of 20 meters per second, the RPM should be at around 23%, with the elevator trim setting set at around 3.5 degrees. The altitude was at around 94 meters. It was found that the lowest speed at which the aircraft could maintain approximately steady level flight was at around 60 meters per second, with the elevator trim set around 17 degrees. The highest speed achievable in steady level flight was found to be around 47 meters per second, with the elevator trim set at around minus 5.5 degrees. Based on the experiment and the graph shown, the frequency of the phugoid was found to be at around 0.074 Hz. Although not showcased due to lack of computing power, the plane departed from the hangar, maintained a steady speed of around 20 meters per second at an altitude of 29 to 32 meters, finished the test circuit, and landed safely in the hangar. The landing has been showcased in the shown screenshot. Thank you for watching. Hopefully, you are now well prepared to undertake a flight operating the Albatross UAV. In the description of this video, I have provided my personal contact information to clarify any doubts you may still have. Happy flying!